Hello, Mr. Ryan, right? Yeah. So I have an array of integer, right? Like 2, actually, no, 4, 16, 64, 49. Okay, just 4
I
numbers.
take 64.
Okay. So these are the 4 numbers. What are those in common?
They are all in the square numbers.
Square numbers, yes, true. Okay, it doesn't have to be square numbers, but let's just take those, for example, for simplicity. This is array, and then we have k equals 2. So we want to perform the operations k times. For each operation, we want to take the maximum of it. What's the maximum?
64.
64, yeah? Okay, what's the square root of it?
8.
Yes? So this is a, right? Okay, so then what do? We erase this one.
Why do you have to square it down?
That's how we define the operation. So for each operation, we take max number and square root of it. If it's not perfect square number, we just take an integer part. For example, 65, we still make it a, right? Because the largest square numbers is 8 before that, right? Am I right?
What if it's
Okay.
okay.
We need to perform another one. So which number we take? Which number we take? Yeah.
Can you have some like decimal numbers?
No, these are positive integer. That's a very good question. Positive integer. Okay, for each one, I take the maximum, I square root of it, if this is n, and I put this back, which is a, right? So I erase this bit, which is a. So what's the next one to take?
49.
Okay, what's the square root of it?
7.
So I get rid of it, 7. Okay. 2 operations. So what's the sum of the remaining? We just add these together. Okay, simple as that.
So 35. What has a k have to do?
K equals 2. Perform 2 times.
Is it 55?
Yes. Okay.
Yeah.
Okay, makes sense. So to sum up,
With the k is greater than a.
that's very good. That's very good. Okay, so we just keep performing. We take a number, take a maximum, we push it back. We take a number, we push it back, right? Does it make sense? So in the extreme cases, all 1. I want to perform a million. K equals a million. So what's the answer?
4.
I take 1, take the maximum, which is 1, right? I square root of it, it's 1. I push it back, it's 1. So it doesn't change, right?
Oh yeah.
I perform a million times. What's the sum after it? 1 plus 1, yeah?
Oh yeah.
Yeah. Does that answer your question?
Sort of.
Sort of, okay. Okay, so what's your solution about that? Is there a trick to do it, or how do we usually solve this stuff?
We just check for that.
We just get, okay? So the key thing about that is how do we get the maximum of an array, common array? How to get...
Sort it.
We sort it, yes, we can sort it. Or, remember yesterday we talked about the find an index, right? Okay, the key thing is that we want to get the maximum, right? We don't need to sort the arrays because we just want the maximum. I just want to know the 49 is the maximum. I don't care the rest is sorted, but sorting is a good answer. We can sort it and get the maximum, right? But we don't have to because we just need to know the maximum. Okay? Define f array k. For I in or for underscore, we don't actually need to use the variable. Range k a dot sort. A dot sort. Okay, A dot sort, and then after sorting, where is the maximum?
On the right.
On the right, which is A minus 1, right? We want to change it to the square root of version of it, yeah? So we can use the math.sqrt. sqrt A minus 1. But this gives the decimal, we can convert it to integer, right? Yeah? Or we can use another function called I squared. I square root. It means that this part returns integer. And then return sum of it. Sum. Hey, that's it. That's your solution. What's the time complexity?
That looks nice.
That looks nice. Yes. What's the time complexity? If you can answer that, that's even nicer. What's the time complexity?
O-N? O-N.
Here is K.
Okay.
Okay. But okay, so here is okay. But what's the here?
LogN.
O(n) log n. Okay?
Okay, LogN.
So what's the time complexity?
Okay, LogN.
Times this together, right?
Yeah.
So O. That's
That's Google.
Okay, OK times n log n, right? And then we need to plus this n, right? So which is bigger? So this is obviously bigger. So we drop the time complexity OK times n times log n, right? Because we need to perform k operation. Each one we need to sort. This is the sorting complexity. Times it together. Does it make sense?
Yeah.
We want to do k things, k times, and for each time we need to do this. So the time complexity is done together, obviously. Okay, this one is the time complexity. Space complexity O1, O1 constant space. Okay, so this is one way, but as I said, we don't need to sort it, right? Most dominant part is this sorting, right? And we just sorted array because we want to get a maximum, which is not very effective. Efficient. Yeah. You want to find the maximum or minimum of a minion arrays, a minion size array. Do you need to solve them? It takes time, right? I can just go through the array. Am I right? Okay. Look here. A minion array. This is a minion. N equals a minion. Okay. I want to find a maximum, a minimum. What's the best way to find it? What's the best solution to find the maximum or minimum of an array? So this O(n) log n, that's what I said. Yes, it works, but it's not the optimum. We just go through this, right? And then we can just find it. The time complexity is O(n), right? 3 to 100,
1,000.
20. What's the maximum?
100.
How do you know it's 100?
It's the biggest number. Because I have my eyes.
Yeah, I know, but how does
It's
the
a
computer?
three-digit number.
How does the computer? Yes, but how does computer find it? You know your sorting is good. You just sort it, right? Your sorting is 2, 3, 20, 100. Okay, the last one is the maximum, but this one is O(n) log n. But how does the computer find it? 3. Okay, the maximum is 3. 2 is not bigger than maximum, so my maximum is still 3. 100 is bigger than the current maximum, which is 3. So the maximum updated to 100. 20 is smaller than 100. So the maximum is 100. Does it make sense? Go through the array once, and that's O(n). Okay.
Heap. I can see my eyes.
So this is the same, yeah. So how do we get it? So we can again go through each time. Current max equals max A. Okay. Look, we get a max, and then what do we do?
Mix.
Short for max. Okay. So we get the max value, and then what do we do now? We need to find where is it, right? I equals A dot, what's the function we talk about? We want to find the index of the value in the array. What's the two functions we talked about yesterday? Index or find. What's the difference between index and find?
Find is that you're trying to find it, and also it could not be there, and the computer won't complain. But index is you're trying to give it index of value, and so you're assuming that the value is there because you asked it.
Yeah. If it's not there, you will return a value error. You'll throw a value error exception. Okay, but in this case, it's there, right? Because I just found it the maximum. It's already there. So both find or index is fine. So now I have index. I just need to change it to here, right? ISQRT. AI, and then return sum of it, right? Make sense? What's the time complexity? K, N, N, yeah, so it's K times N, right? This is 2N, OK times 2N, which is OK times N, and plus N, plus N, yes. But obviously this drop the trivial part, so it's OK times N. Which is better? This one or that one?
That one.
This one, yeah. Because look, OK times N, and this one, additional terms, which is bigger than 1, okay? So this is like that. So we talk about a data structure, which is taking the maximum or minimum from a queue. We call it, what kind of queue? Remember queue, first in, first out, right? But if it's first in, priority out, max out or minimum out, what do we call it?
A nice queue.
Ice queue. Yes, it's priority queue, but it can be implemented using a heap. Heap is a binary tree, right? Remember the binary tree. This is 1, 2, 4, 8, 100. So always this is the minimum. This is called min heap. Right? The min heap. And if this is the maximum, like 100, and this is 2, 4, this is 1, this is 0, then this is called max heap. So it's kind of like a binary tree. It's called binary heap. A binary tree, that the root is always the minimum or maximum. Okay?
Yeah.
Okay, this is called heap. And we can use that. The thing is that
The heap should have a maximum always ever, because a heap is like a hill, and if a minimum was at the root, then it would just be a hole.
Yeah.
Not a heap. A heap is kind of like a hill.
Yeah.
A hill. So the maximum should be on the top, but if the minimum is on the top, then it's just being a hole, not a heap.
Yeah. I understand your point. Yes. Okay, so we can transfer between min heap and max heap.
I'll show you.
Okay.
So a heap is like this. The maximum is at the top. If the minimum is, it's just gonna be a hole.
Yeah.
Hole.
True. Okay. Yeah, that's very good. In Python, the heap is min heap, meaning like, okay, so if I turn an array to a heap, when I heap push, heap pop, it's always getting the minimum, right? But in this case, we want to get the maximum. So, and these numbers are all positive, right? So how do we turn the positive numbers into the, min heap? Right? Look, 2, 3, 100. If I do the heap pop, and you give me 2, right? How do we change it to give me 100? There are 3 numbers, right? In Python, it's heap pop. When I do heap pop, you give me 2. Is there a way to make it give me 100 instead?
Heap pop, right?
Oh, no, it's not heap pop, right? But we can do
Heap
something.
pop. Heap pop. Heap. Heap pop on the other side.
In Python, there's no heap pop on the other side.
Max
Heap pop, right? I don't know.
Max
Okay,
heap pop.
but no, I'm give you a hint. How about this number positive? If I change it to,
Negative.
then what does it become? -2, -3, -100. What's the minimum of it?
Minus 100.
Okay, and then we just negate it. Does it make sense?
Neglect it.
Yeah, negate it. Does it make sense now? Yeah. Obviously, we need to turn the numbers into heap, right? So, but we need to get this. A equal, we change to minus, yeah, because it's all positive. Minus I for I in A, okay? Look, A, I change it to minus. Negate each one. Minus I for I in A, okay? And then now I need to heapify. Heapify. What's heapify? What's this mean?
Make it a heap.
Excellent. Make it a heap. So heap I, A, and I change this array into heapify. Okay? And then now I can go through this K time. For K, for underscore in range K. Okay? And then I need to take it out. So V equals heap pop A. Okay? I take this out, which is the negative. I need to make it positive again, right? Does it make sense? Yeah? Heap push A minus V square root of it. I square root of it. And then I need to negate it again. For example, like minus 100, I take it out, it's minus 100. I need to make it 100. I need to square root of 100, which is 10. I need to put the minus 10 back into the heap. Alright? That's what it means. So V equals heap pop, and I can actually put a minus here, right? And then here that will become ISQRT V. Put the minus here, right? And then sum, return sum A. Okay, so is that correct?
Put make it back to positive.
Minus, yes, exactly. Well done. Okay, time complexity. Heapify, okay? The key thing about the complexity here is the heapify. If we are making a heap directly by giving it a list of elements, n, the time complexity of heapify is O n. Okay, the time complexity of poop and push is log n. Okay, so the time complexity is O(n) plus k times, right? LogN. Okay, and then plus this sum, which is O(n). Okay, actually O to n, right? Droplet constant. So the time complexity is O(n) plus k times LogN. If we are building a heap by pushing n elements to it, the time complexity is O(n) log n. The time complexity for this one is O(n) plus k times log n. Okay, so which one is better? Space complexity. Obviously, this one is O(n). We need a space. This is time complexity. This is space. The sorting one. The time complexity is k times log n, right? We talk about space complexity O(1). Eric, is that true? Your approach, sorted. K times O(n) log n, right? The second one, finding the max. Finding the max index method. The time complexity is O k times n, right? Yes. The space complexity O(1). The third one, using the heap. The time complexity is O(n) plus k times log n. Okay. The space complexity is O(n). Okay, so which one is better? Come on, which one is better? By looking at the tables. Which one has the optimum time?
The bottom one.
The optimum, right?
Heap.
This one obviously is better than the one. This one and this one. This is OK times n. This is OK times log n. Okay? So obviously this is better. Yeah, space complexity, the second one is
You
better.
always save the best one till last.
Yeah, but this one has the additional O(n) space, right? Because we need a heapify. If we can,
It has n space.
okay, so let's, this n is question now because we are modifying the original array, or do we? We can modify the additional array. We don't need to use an additional array. Okay, we can just go through this A and then change each number to negative and heapify. Then in this case, we are not creating additional array. We're just modifying the input array. Then it probably is O(1). Okay. Okay, so the thing is that for this sorting, okay, we consider is the O(1) space. Okay, usually the sorting algorithm, the quick sort, remember additional array, right? How do we quick sort? Remember? How do we quick sort? We pick a number 3 in the pivot number. What numbers are smaller than 3? 2 and 1. Put it on the left. What numbers are bigger than 3? 4 and 100. Okay, so now 3 is here, right? And then we keep recursively sorting the left part and right part. Okay, so what have you learned today?
About this thing that we're trying to like squaring it.
And put it back. Yeah, we want to perform k times. So what are the solutions you learned? And I just describe one is enough.
One of it is sort, which is one is.
One of them is heap,
Yeah, okay.
which is the
And
farthest.
one of them is index.
So if we want to find out the maximum or minimum of an array, do we have to sort it? What are the best solutions to find the maximum or minimum of an array? What's the optimal solution for that? You want to find the maximum of an array.
Heap.
Just linear, right? Okay, that's it for today. Bye bye.
Bye!